So this session is about authenticated encryption, and there will be 3 talks. The first talk is multiplex TBC-based authenticated encryption with sponge-like rate by Yaobin Chen, Thomas Peter, and Francois Xavier Standard. And Yaobin Chen will give the talk.
This is the for introduction. So today I'm going to talk about a new AED design. It's called multiplex. Yes, mostly it's a leakage resistant AED, and this is joint work with Thomas Peter and Francois Xavier Standard. So I will introduce some background. So AED is a symmetric primitive that can ensure both the data integrity and data confidentiality at the same time. So typically this may be some, we can divide the AED maybe in 3 parts. First part is the maybe take input as long as the key and produce the sub key for the following message processing. And then it will encrypt the message and produce a ciphertext. And finally, we need to authenticate maybe the ciphertext to produce the final tag. And in the domain of the physical security, that if you want to have protection against the maybe side-channel attack, one of the popular options is to use the masking. So somehow maybe we need to maybe if we and any nice idea is you need to mask or publish this AED. This method maybe it works, but sometimes it's not efficient because it will introduce some maybe significant overhead because we need to protect all components of the AED, especially if the message is very long. So there's maybe some clever idea that's called the level interpretation. That's proposed by Khairallah in the CCS 2015. Then we can avoid equally protecting all parts of an application. But before that, we need to identify the protection level of each part so that we can have some performance gains. So actually, it's mostly from the implementation point of view, but now we initially achieved in 2017 and also for AED, but at this point they only consider for integrity. So from this idea, so for integrity, typically maybe we only need the strong protection on the key derivation function, maybe the first part and the last part for the tag generation function. And while for the main part, usually maybe the part that processing the message blocks, usually for the integrity, we can allow the unbounded leakage for the rest. So by from this idea, it's clear that we can achieve some substantial performance gains for integrity if we use the masking to protect against the side-channel attack. And from this slide of research, I think in 2020, there's also it's mostly for the least lightweight cryptography competition. So for the one-pass modes, there's also some security definition in the leakage setting. I think for the one-pass mode, we can achieve is the CIM2 and the CCIM1 security. And for CIM2 is the integrity in the leakage setting. So the name is a ciphertext integrity with long misuse resistant and leakage in both encryption and decryption. And for the confidentiality is the CCA with misuse resilient leakage in encryption. I will not go into detail to explain this notion, but it's mostly some trade-off between the implementation and the security definition. And for the least winner ASCON, actually is explicitly follow this idea. I mean, maybe to achieve the integrity in the against the sanctional attack, we maybe need only the DPA, the differential power attack protection in the key generation function, tag generation function, which corresponds to maybe only the first permutation call and last permutation call, which involve the key binding. So this is the sponge-based design. And while for the TBC-based design, that's based on TBC, there we don't have much options. The one that's proposed in the appendix of the TDT paper is you can see this picture is based on TBC, and the red is 1/2, which imply to handle the ambient message block, it requires two TBC cores. Which is maybe not as efficient, because then we need to TBC to process one bit message block. Yeah, and so so there's also another design that's proposed in the Trace 2022. It's a triplex. Essentially, the motivation of triplex is to improve the rate of TET. So the rate of triplex can be 2/3. So which means that to produce the to handle two ambient mesh block, it requires 3 TBC cores. And the underlying primitive is the TBC with ambient key and 2 ambient tweak. So this is mostly the state of the art regarding the TBC-based design for the leakage-resistant AAD. So the natural question is that can we improve the rate of the triplex, which is based on the TBC? Because as far as we know, for the sponge construction, actually the rate or the capacity in the sponge, it can be very flexible. It maybe you can adjust depend on the size of implementation, and also depends on your maybe your security goal and or efficiency. You can somehow to adjust it. So our initial idea is can we improve the rate of triplex to make it more flexible instead of just fix some maybe 2/3. So here is our new design that is called the multiplex. I think the main advantage of multiplex is allows more flexibility, and it can also achieve this almost the same security level of the previous design triplex, the ambient CIML2 and the half ambient, there's a typo of CCIML1, and also standard ambient security for the confidentiality. So here is the picture of the multiplex. Actually, we compare multiplex with triplex. I think that one of the clear advantage is that multiplex can allow a more flexible rate. Like the rate is D/D+1. So if we have but the underlying primitive TBC should have a large tweak, while the previous triplex, the rate is fixed is 2/3. Yeah, and also actually, there's also naive approach to extend the triplex to have a more flexible rate, but maybe by simply increase the tweak size of TBC. But then actually for the triplex, for each iteration to handle messages, the TBC is invoked in somehow sequential mode. We need to invoke the first TBC and to produce the tweak, and then we can invoke the following TBC core with this tweak. So for the multiplex, actually in each iteration, maybe all of the many TBC core can be invoked in parallel. So this will have more efficiency if we have more when we have a better rate. Another difference is that the lungs in the triplex, the lungs actually appear in KDF and also in each iteration of the message in each iteration to handle the messages. Initially, this is to guarantee the security in the proof, and we also find actually the lungs may be only required at the first TBC core, while the rest we don't need to put the lungs to improve the security. So actually in the triplex, the lungs only appears in the first TBC core. Yes, so from this idea, if we want to obtain a better rate in multiplex, you can use the TBC with the larger tweak, and then we can increase the number of TBC core in each iteration. Yeah, so we can also maybe make some trade-off between the security level we want to achieve and also efficiency regarding the rate. Yeah, and actually the main component of the multiplex actually is the multi-hash. So actually, the main idea is how to turn a compression function or a hash function into how to encrypt and authenticate messages. So here on the left side is especially the right part is the high-loss double block compression function based on TBC, and we extend it to maybe for output multiple blocks. And we use this extended compression function to encrypt and authenticate the encrypt message and then authenticate the ciphertext. So here is how it works. So actually, we simply use the output of previous iteration to extract for the last one to use this output to XOR the message and produce the ciphertext. And then we simply put this ciphertext as the trick in the iteration of this TBC. Yes, so by using this idea, for each iteration, we somehow encrypt the message and then encrypt and make. And the block here is the example for block. We can output multiple block. It's similar to so that we allow us to have a flexible rate. And so here is the whole picture of the multi-hash. Actually, the main component they handle the messages. It can output multi-block in each iteration. But actually, the collision resistance of this construction is on n bit because actually only the middle two n bit state they cannot be manipulated by the adversary. While for the trick size, the trick of TBC actually can be somehow for the decryption, because in the CC attack, because the trick here is used to authenticate the ciphertext. So for the trick here, it does not provide security, and so the security of this multi-hash is essentially rely on the 2-bit state. Yes, so this is the main component of the multiplex. It essentially use the hash function to handle encrypt and authenticate the message. I think there's also one idea like previous triplex. I think also multiplex can have somehow the committing security, because the committing attack is similar to the collision attack on the AED, but here the design component is the hash function, so you can somehow achieve the collision resistance and also the committing security. And so for the security level, for the integrity, it can achieve for n minus log n dm bit for the integrity of CIML2 in the unbounded leakage model. So actually the integrity can hold if the query is less than to the n over dn. And for the confidentiality, there's some separation. For the confidentiality in the leakage setting, it can achieve the half n bits. And for the confidentiality without leakage in the lungs misuse resilience setting, it can achieve almost n bit is exactly n minus log n and dn bits. So here is a table for the parameter from multiplex, and it is based on the TBC with n bit key and dn bit trick. So maybe like the security key will be n bit, trick size should be dn bits, long size can be n bits, and the maximum block length can be 2n over n, and the tag size can n bits. Security level will be n minus log n dn, and the red is related to the size of trick. It can be d over d plus 1. And so here example for skinny 384. So if we use the skinny 384, the red can be 2 over 3. And actually the red can be improved if we use the TBC with large trick, like the recent Doxy TBC 512. The red will become 3 over 4. And for the Doxy TBC 640, the red can be 4 over 5. And so if in the future, maybe if there's some large trick TBC, the rate can be also adjusted accordingly. And so this also maybe strikes some discussion, interesting discussion, like the previous sponge-based construction like duplex. So as far as we know, the rate can be increased if the size of permutation is increased. So we can have a very flexible rate between the trade-off, the security and efficiency trade-off. And for the multiplex, actually we can achieve the similar property. So the rate actually can also be increased if the tweak size of TBC is increased. So this is the main component multiplex. So it may have some interesting questions. So how security and maybe the number of rounds of the underlying primitive, like permutation or TBC, will scales in function of the tweak and permutation size in order you want to compare to this kind of different design based on different primitive, because now they can have similar flexible rate. Yeah, so here is the conclusion. So in this paper, we propose a new AAD design they call multiplex. They can allows more flexible design than the previous triplex, and it is based on the TBC, and it can achieve a similar flexible rate as the sponge-based design. The rate will be the D over D plus 1 for TBC with DNB trick and NB key. Yes, that's my talk. Thanks.
So any questions? So I have one question. So related to slide 13. Yes. So in case of deoxys, there is already like some difference in the number of rounds between the different tweak sizes. So did you look a bit about how the rate versus the number of rounds?
Yeah, I think typically if the number of rounds will increase if the types of tweak increase.
At some point, if the number of rounds decreases, the benefit in terms of rate becomes maybe not too much. Did you look at that?
Yeah, we don't check in because I think these two designs quite new for the Doxy 512 and 640. Yeah, but we expect it maybe there will be more discussion between these two different design based on different primitive.
Okay. Yeah. Any other questions? Well, then let's thank the speaker again.